All right, so in lecture A, we talk about line integral of scalar field. When you calculate that, you actually get something called the surface area of some functions. Now, when we move on to lecture 9, line integral of vector fields, what we actually calculate is the work done in moving an object from one position to another position inside a vector field. So we study the work done moving an object from one point to another in dot product when you study dot product two. But now we put ourselves in a more realistic situations that the work done moving an object inside a vector field. For example, when you try to move a table outside in the windy environment, what's going to happen? Okay. So we're going to explore that. We're going to derive a formula to calculate the work done in moving an object from one position to another position inside a vector field. But for short, from now on, I'm going to say line vector field, and hopefully you understand that idea is you want to calculate the work done in moving an object from one position to another position inside a vector field. Okay. Now, so that's the objectives of the course of this lecture. That we look at the line integral of vector field. We're going to derive the formula to do just that. Then later on, we're going to apply the formula to some examples, and I'm going to show you some simulations to actually visually explain what we have with the result that we got from the algebraic calculations. So before we dive into showing derive the formula for the line integral of vector field, I'm going to give you some definitions. It's important to have definition because now we dealing with vector field. When you have vector field, that means you need some directions. All right. So for you have some curve here, and it's now really matter when you go from one position to position, the directions in what direction in which you move, it really matters, right? Especially when you have a close curve like this. If you move it counterclockwise or you move it clockwise, it will give you a different sense. Okay. So the first definition is orientations of a curve. So line integral of a vector field requires the directions of the curve. Usually that we call orientations. So orientation is a specific directions along a path. At C. And this directions is considered as the positive directions of the curve. Or of the path. And when you impose such conditions or such direction into the path or into the curve, you have something called the oriented curve. So the curve C or the path C is an oriented curve. So this first image is the oriented path from P to Q. So but this one is very similar to the definite integral that we usually do, because the integral we usually go from A to B for B is greater than A, usually from left to right. That's the direction, that's the positive direction that goes. So in this case, you move along, you can have a particle and this particle move along this path from point P to point Q, so that's positive. So in this case, this is called the oriented closed curve. And usually, but not always, usually we say that this is a positive direction as clockwise directions, and clockwise is the negative directions. So this is the closed oriented curve. So that's the orientations of the curve. Now we're going to move on to the definitions related to work done. Some of this you have seen already in lecture 2. So the work done is how much energy is provided to move an object from one locations to another. And if you took a physics course in high school or in your first semester here, you have the work done by a constant force. Is actually equal to, yep, force times distance. Very simple. And this one is the regular. So I want to point that out. This is regular multiplications. So in this case, my theory work done by constant force. I want to give you a note here that the force is directly applied along the line of motions. So most of the time we kind of just push the table directions, and the force that you apply, constant force that you apply is also in the force. Yes. But obviously, in reality, that's not going to work. Carry a table, which will be always applying the force at an angle. Right. So suppose that the force is applied at an angle. So force F is pointing in some directions other than the line of motions. Yes.
Why is this force vector and not the force constant?
Can I write that formula and then answer the questions? So the work done is F dot with D. Okay. So this is the dot product. So you agree with me that's the dot product, and from the dot product you have the work done is equal to F dot with D. Right. Because when you analyze the force, right, some of the force get contributed in the vertical direction, which is not the line of motion. And part of it will apply into the line of motion. So that's why when you write down the details of the dot product, you have the magnitude of force times the magnitude of distance times cosine of the angle between the two vectors. Okay. Now, if you move that in the line of motion, F and D, the angle is going to be 0. So therefore, this is 1. So therefore, usually we just write F times D. You with me? Okay. So in a way, this is a more general formula for most of the situations. So now we have the work done, we have the dot product. We're gonna put this in a vector field. Okay, let's see what happens. So this is the situations you have a work done in a vector field. You have the XY coordinate system. You have a path moving from one point to another point. We want to move the object, let's say it's the black dot that we want to move along this C. So I want to know this is C of A. That's the starting point, and this is C of B. Is the ending point. All right. So let's see, you have this particle or you have this object in black. Okay. You want to move this particle along the path, along the curve C. Okay. So let's say we consider this point. So at this point, obviously, we want to move this black dot along the path. So you have two things, right? You want to move along this path. So that is the distance directions. So this will be represented as a vector. It's called tangent vector. Tangent vector. Tangent, which will tell you the directions of this point. And then you have some force applied on the particle. You with me on that? So there's two forces very similar to what we have with dot product. One is along the line of motion, the other one is the force that applies on the object. So here you have, this is F and this is T. So this, we consider the unit vector. So this unit vector, unit tangent vector, this is very similar to the distance right here, right? Just the line of motions. Now, because we don't move along a straight line anymore, we move along the curve, so that's what we want to have vector, the tangent vector involved in the motion. So now I'm gonna zoom into this particular point and bring it out here and analyze the force a little bit. So I have this one is unit tangent vector, and this one is the force one. And this one is the angle between the two vectors. I call that theta. Now suppose you have f of x comma y equal to p of x comma y I plus q of x comma y j. Suppose this is a vector field where p and q are scalar fields. So again, scalar field is just the real value functions that the regular functions that we are doing. So what we want to do here, so we want to calculate the work done by this vector field F in moving an object along a smooth curve C. So this particular condition is important that we consider the smooth curve C. All right, so a smooth curve means that it's differentiable. When we talk about differentiability, that means the smoothness of the curve. So we're gonna approach a similar, gonna do is apply a similar approach that we did when we derived the arc length, when we derived the line integral of the scalar field. What we're gonna do is that instead of just a curve, gonna break the curve into different points, and we consider the work done by every point. Then we add all the points together. We add all the work done together, and then increase the number of points along the curve to infinity. The limit of the summation, and that is the definite integral. So next we divide the curve into n pieces. The nth piece of the curve has the displacement of delta Ri. Sorry, the ith, not the n, the ith piece. All right. So again, this is very similar to D, the line functions. Now the next assumption is quite important. If the piece is small enough, then the force on the eyepiece is approximately constant. We get to this later, if you may wonder why you have the unitary factor here. We get to that. So bear with me. Right, so the work done by the force F along the I piece is, right, so I do delta W sub I is approximately equal to F sub I dot with delta R sub I. So this is just one piece along the curve, and you use the dot product. Now the total work done on the curve C so let's say you have n pieces along the curve, and you break the curve down into n pieces, and you approximate the work done along the I piece. Now you add all the approximations together, and you have W sub I is approximately equal to the summations of F sub I dot with delta R sub I for I going from 1 to n. Yes.
What is total work on the curve still seven?
One more time.
Like the total work on the curve, why is it still more than W sub I?
So because you count,
Okay.
so W1 plus W2 plus W. Now to increase the accuracy, of the approximations, we increase the number of pieces to infinity. That is, so now the work done is no longer an approximation, it's become an equal sign. So W is equal to the limit as n go to infinity of summation for I going from 1 to n of F sub I dot with deltas R sub I. All right. So as we know, we never want to work with the limit of the summation. We turn this into a definite integral. So the definite integral along the curve C or along a path C of F dot with dr. So the limit of the summations becomes integral. So this is the path integral on the line integral. F sub I becomes just F. The product remains the same. Delta Ri becomes dr. Okay, good. So that is the line integral. It move the line integral of vector field. Any questions? The what come from? Dr. Okay, so delta R. Dr is just very small. Like just like delta x, and you turn that into x. Here is the same thing. Delta R means the difference between 2 points along the curve. but now the difference is very small, it's become zero. Right? Okay. All right, so theoretically, this is the line integral vector fuse, but in practice, it's a little bit hard to just use this formula and calculate the work done, because we don't have enough information to do so. All right, but let me know this is the line integral of a vector field along the along a smooth curve C. Space. Everyone said. I look at your work, your handwriting. Oh, I mean your spacing, because I forgot to mention. Need a little space here. In the practical case, all right. So in practice, we're going to use a different formula here to calculate the work done in moving an object from one point to another point inside vector field. So here, but we see this before that dr dt is equal to r prime of t, or we usually do dr is equal to r prime of t dt. All right. So what we're trying to do is that instead of calculating the line integral of the vector field along the curve C, that depends on the curve, the entire curve C, we're going to rewrite the formula so that our formula depends on the parameter T, right? Because usually the curve is parameterized using some parametric equations. So then W becomes the definite integral from a to b of f dot with r prime of t dt. So this is, in practice, we're going to use this formula to calculate the line integral of a vector field. Now we can actually stop right here with the formula, but I want to go back to the beginning of when we look at the graph and why we have tangent vector right here. So we're gonna continue deriving the formula so that we're gonna make the tangent, the unit tangent vector show up in our formula. But again, in practice, this is the formula that we're going to use. How can I make a square here? Good. That's the formula. Right. So from this formula, what we're going to do is we're going to multiply and divide by the magnitude of r prime. So by doing this, you have r prime over the magnitude of r prime to be the unit tangent vector. And you still have the magnitude of r prime of t dt.
T and magnitude of R prime, would you do that multiplication first, or would you do the dot product?
Um, it doesn't matter, right? Why that is the case, because it's dot product. Okay. There's one of the problems in the dot products that you have that if you take the dot product and you multiply with this is a scalar. Okay. Gonna give you the same answer if you take the scalar and you multiply with either of the factor and then use the dot product, it's going to give you the same answer. All right. So this is a little bit of a mess here that we need to clean up. If you remember when we talk about arc length and we derive the arc length function formula, we have that the magnitude of r prime of t is actually equal to ds dt. I assume that you remember it. Yes, totally, right? Totally. Right. So this is the formula that we're going to apply here. So instead of the SDT equal to the magnitude of r prime, we're going to derive or rewrite this as the magnitude of r prime of t times dt. Okay, so this is the mess that I'm talking about. So we're going to replace this as ds. And when we replace this, the parameter with ds, that means depend on the arc length. When it depends on the arc length, is no longer the definite integral, but just the line integral along the curve C. You with me on that idea? So here, f dot with t ds. All right. With the idea again that we're going to apply the arc length functions that we cover in, I say, like lecture 4. All right. So r prime, the magnitude of r prime of t times dt is not times, kind of approximate, but times dt is actually equal to dx. You with me on that? All right. So again, this showed that why in the graph we have the unit tangent vector along with the force F, okay, because of the derivations that we have. And this definitions right here, or this formula right here, usually the definitions of the line integral of vector field, because it takes into account not only vector field, but also the tangent vector to tell you the directions on which particle is moving, and along the curve C is more clear compared to the derivation study. You okay with this? All right. Now we're going to use this formula and apply it to some situations here. For example 1, you have the vector field of the point x squared comma negative xy. And you want to find the work done by this force field in moving an object along a quarter circle. And this quarter circle is parameterized using the formula. Right. So the first component is cosine of t, the second component is sine of t, and the parameter is going from 0 to pi over 2 only because it's the quarter circle. You okay with that? Okay. I'm going to apply the formula that we just derived right here. All right. So to calculate the work done, by F, we do, right, so F dot with r prime of t dt for t going from A to B. So this is the work done where A is equal to 0, B is equal to pi over 2, and we have a few things that we need to consider here. So the curve or the path that we have is parameterized using R of t, right? And you have R of t equal to cosine of t comma sine of t, or R prime of t is equal to negative sine of t comma cosine of t. So we have R prime, we have value of t parameter. We need to take into account f as well, but remember, we need to put f in parameterized form. Okay. So x is equal to cosine of t and y is equal to sine of t. You write that in the term. You have f is equal to x squared comma negative xy, or cosine squared of t comma negative sine of t cosine of t. Now you know everything is substituted into the formula to calculate the work done. Then you have the work done is equal to the definite integral from 0 to pi over 2 of f, which is cosine squared of t comma negative sine of t cosine of t, dot with r prime, which is negative sine of t cosine of t dt. So this is the dot product, should be hopefully simple enough for us. So negative sine of t cosine squared of t minus sine of t times cosine squared of t dt. Right. So I got this integrand from the dot product. And we go at 12:15. Yes. All right. I want to finish this problem. We almost finished. So this is the line integral from, sorry, the definite integral from 0 to pi over 2 of negative 2 times sine of t cosine squared of t dt. And this definite integral can be solved using integration by substitutions. Right. So you let u equal to cosine of t, and du is equal to negative sine of t dt. And you make a table to change the limit of integrations. T equal to 0, u is equal to 1, t is equal to pi over 2, u is equal to 0. So the definite integral becomes, so I take out the negative 2, that negative 2 times the integral from 1 to 0 of negative u du. U squares. Yes, yes, thank you. U square. Yes.
Why can't we just leave the negative inside and only we have the negative sign?
Because I want to distinctively show the two negatives so that we can use one negative to flip. Alright, so we're gonna use this negative to flip the. So -2 times the definite integral from 0 to 1 of u squared du. Zero.
I see it here.
Right, so you have -2 times uq over 3, evaluate at 0 and 1, and you should get the answer to be -2/3. So now, with your intuition, does it make sense to have a negative number? Yes or no? If yes, why that is the case? All right, so I'm gonna show you the simulations of this example, and hopefully from this simulation, you understand why that is negative. Okay. All right, so the arrow in black is the vector field that we are working with. This is the part of circle that we are considering. So this is the particle or the object that we want to move from this point to another point along the part of circle. All right, so now let's see the simulations. Because you move in this direction, this is the positive directions, but the vector field is moving in the negative direction or the opposite direction. So therefore, you need a negative work done, right? So it's moving against the vector fields. Therefore, you have you with me on that? All right. So in practice, when you answer the question, answer for this example, you're supposed to have a positive work done. Bear with me here. But because of the directions of the motion, move in one direction, the vector field move in the other directions. That's one. But when you consider a circle, it's always positive counterclockwise and negative. Most of the time, unless they specify it. But without specification, you always go counterclockwise. Good. Having fun today, hopefully. Yes. All right. Thank you for being here, everyone. I will see you Thursday. So last time we continue with light integral of vector fields. So we derive a formula to calculate the light integral of a vector field. That is the short answer to say that you want to calculate the work done in moving an object from one point to another point inside a vector field, along a path inside a vector field. So we get the formula right here. There's a lot of formula in this particular page. This is the definition. We're going to look at this definition a little bit later. But in practice, what we use is we use this formula to calculate the work done. So this is the definite integral of the vector field dot with the vector tangent vector. And it depends on t. We did one example. So in this example, we calculate the work done in moving an object from one point to another point inside the force field of that form x squared minus x squared comma negative xy along the path. This is the quarter circle. And we get that the work done is equal to -2/3. So I show you the simulation, and it's show that the point or the particle inside the vector field is moving along the path against the vector field. So that's why you have to make it here. The work done is should be positive, right? The negative is there to say that okay, you go in against the vector field. So the formula that you see here can be described in different forms, depending on the context that we want to look at. So I want to derive those formula here in the next page. So different formula for work integral. All right. So in this derivations, I'm gonna show you in three-dimensional using three-dimensional vector field. So I have that F is equal to Pi plus Qj plus Rk. And the curve C is parameterized using also a three-dimensional three-dimensional vector field. So that is, so C is parameterized as R of T equal to F of Ti plus G of Tj plus H of Tk. So by definition, you have the work done to be equal to the integral or the line integral of F dot with T ds along the path C. So this is the definition. So this definition is actually derived, our derivation is above, right? So it's very similar to the work done formula that we did when we talk about dot product. Right? So this is the force applied on the object, right? And a T in this case, the extension vector, that is the line of motion. Right? So you use dot product for the small piece along the path. And then you take the summation for all the pieces along the path. And then you take the limit as n go to infinity. You increase the number of pieces to infinity, so that you have this the line integral. Now this formula is actually also equal to F dot with dr. And this formula is called the vector differential form. Again, let me remind you what we have in the derivations. So this is our derivations. Okay, this is what we got. And we say that dr dt is equal to r prime, or in other words, dr is equal to r prime dt. So that's what the differential form in our equation. But again, of course, in practice, what we use to calculate the work done is the definite integral from a to b of f dot with r prime of t dt. And this formula is called the parametric vector evaluations. Right, it's why parametric equations? Because everything is written in terms of parameters. All right, so I'm going to use this formula right here and derive on the formula. So F depends on P, Q, and R. And R it depends on F of T, G of T, and H of T. All right, so this formulas become the definite integral from A to B of P, Q, R dot with F prime of T, G prime of T, and H prime of T, and dt. Now you apply the dot product here and you get the integral from a to b of p times f prime of t plus q times g prime of t plus r times h prime of t dt. And this formula is called the parametric scalar evaluation because it does not depend on vector anymore, but depends on the scalar function. So this is parametric scalar evaluations. Now, from this integral, if you break the big integral down to three smaller integral in terms of f prime dt, g prime dt, and h prime dt, then you can have a different formula with different names. So I'm going to rewrite this formula as the integral from a to b of p times f prime of t dt plus the integral from a to b of q times g prime of t dt plus the integral from a to b of r times h prime of t dt. All right, so f, g, and h are the components of the vector value functions r of t, right? So r of t is equal to f of t, g of t, and h of t. In other words, it can be written as the first component, or x is equal to f of t, y is equal to g of t, and z is equal to h of t. You okay with that idea? All right. So therefore, when you take the derivative of x, so you have dx dt equal to f prime of t. You agree with me on this? Right. Instead of this, you can actually write this as dx equal to f prime of t dt. You're okay with this? You know where it's coming from. Okay. And you do the same for the second component and the third component. In other words, you have dy is equal to g prime of t dt, and dz is equal to h prime of t dt. Okay. All right. So now instead of writing like this, p times f prime of t dt, I'm gonna substitute that with dx. Instead of g prime of t dt, I substitute that with dy. And h prime of t dt, I'm gonna substitute that with dz. And I have another formula from the list here. That the integral of p times, integral of p dx, but now is no longer the parameter t going from a to b. You're moving along the curve c. So this integral is the line integral. It's no longer the definite integral. You have the line integral of q dy plus the integral of r dz, and moving along the path c. And this one is called the scalar differential form. So you have kind of a 5 different formula. It depends on the context that you're talking about. You may use an appropriate formula for that particular context. Right. So again, in practice, for definition, you use one formula. In practice, you use different formula. You want to focus on just the scalar function, then you use parametric scalar evaluations. So this one, this scalar differential form, you're going to see that in different lectures on the Green's function, the Green's theorem that we're going to cover after the test. All right. Any questions on this derivation? Straightforward. Yes. All right. Again, it depends on the context. You have a different name for the same formula. So you're going to see that we're going to use the same formula for something called the flow integral or circulations, in the context that you have a fluid situations. So for the flow integral, if R of t parameterize a smooth curve C in the domain of a continuous velocity field F of a fluid flow then the flow integral is, right, so I call this flow equal to the line integral of f dot with t ds along the curve C. So this is the flow integral or just the flow. So in this context, if you in practice, if you want to calculate this integral, you use the formula that we see earlier here. This is the this formula right here, the parametric vector evaluations. Okay. And because in practice you use the parametric vector evaluations, you need to know the starting point and the end point. So the starting point here, the flow moves along the curve C from the point A equal to R of little a to the point B equal to R of B. So that's the flow integral. Now, in a more specific context that you have a closed path, right? So that the starting point is equal to the closing point. You move along a circle, for example, or along an ellipse, something like that. Then the flow integral become a circulation. Okay. So a circulation is also using the same integral. Right, bear with me. Just write out the homework. And I want to introduce new notation, please. Right. So this notation is this. To indicate that we take the line integral along the closed path. So when you're doing this, when you calculate the circulations, this indications that the starting point and the ending point is going to be the same. So where capital A is equal to capital B, and capital A, capital B is the R of A equal to R of B. So this a little bit overview here with a lot of explanations, but when you look at this formula, you understand that we do the calculation for the circulations because the line integral will be along close path. All right. So now we're gonna use this formula again to calculate the circulations. Okay. So in example 2, you have the vector field of the form x minus y, comma x, and you want to calculate the circulations along this vector field. Along the circle, parameterize as cosine of t, sine of t inside the vector field. So the circulations formula is equal to the line integral of f dot with t ds, and this path or this curve is a closed curve where c is parameterized as r of t equal to cosine of t sine of t. All right, so this is the entire circle. How do we do the circle? Because t is going from 0 to 2 pi. So that's just the formula. Again, in practice, you use a different formula to calculate the circulation or calculate the work done. You use the parametric vector evaluations. That is, the circulations is equal to the definite integral from A to B, in this case from 0 to 2 pi of f dot with r prime of t dt. So now our task is to write everything in terms of the parameter t. And so you have r of t by r prime of t, where r prime of t is equal to negative sine of t, cosine of t. And even for the vector field f, even though you start out with x and y, you need to parameterize that as well. So x is equal to cosine of t and y is equal to sine of t. So f of t is equal to x minus y. So that is cosine of t minus sine of t, comma x, which is cosine of t. Then you have the circulations to be the definite integral from 0 to 2 pi of f, which is cosine of t minus sine of t, comma cosine of t, dot with r prime, in this case negative sine of t, cosine of t dt. Okay. So you apply dot product here for the integrand. the integral from 0 to 2 pi of negative sine of t times cosine of t minus sine of t plus cosine square of t dt. All right. Now you distribute negative sine of t and then basically manipulate the integrand again, see what you got. Yes.
Oh. Not like a definite interval.
Right. When where you have the curve. So without the circle here, that means it's the regular path holding. But when you include this circle, that means a closed path or the closed curve. So this become negative sine of t cosine of t plus sine squared of t plus cosine squared of t dt. All right. And you have the identity here, sine square plus cosine square is 1. Then the definite integral becomes integral from 0 to 2 pi of 1 minus sine of t cosine of t dt. Can you evaluate this integral, please? It should give you a very nice number. What is the integral equal to? The whole thing?
Yeah.
It's not going to be 0 for the whole thing. All right. So you separate into two different integrals. So the first one, integral of 1 with t, is not going to be 0. It should be 2 pi. The second integral should be 0. So here, if you rewrite this as the integral from 0 to 1 of 1 dt minus the integral from 0 to, to 2 pi of sine of t cosine of t dt. So the first one is easy. It's going to give you 2 pi. And for the second one, if you use integration by substitutions, you will get 0. And there's a trick that we're going to learn later on in this course, that if you integrate an odd function over a symmetrical domain, it'll be 0. Look at it. So this is an odd function right here. Sine is odd, cosine is even, so therefore the product is an odd function. 0 to 2 pi is a symmetrical domain. So therefore this integral is going to give you 0. So either integration by substitutions again, or the argument that you integrate an odd function over a symmetrical domain, then you have 0. So in this case, the circulation you have is 2 pi. So this calculation suggests that the fluid circulates along the circle counterclockwise. Why is counterclockwise? Because like if you don't have the figure, you can still conclude that the circulation of the fluid circulate along bound the circle counterclockwise. That's right. And by definitions or by conventions, the counterclockwise is always the positive direction for the unit circle or in the circle for that matter. Okay. We good? All right. I want to show you the simulations to again conclude this this problem. All right. So you have a fluid particle here is moving from circle. So the circulation that will give you a positive number. We good? Okay. Now let's move on to the last example. All right, so the last example. So in this case, you have a fluid velocity. This form, three-dimensional vector field, and find the flow along the helix, right? So it's not going to be a closed curve anymore, but you're moving along the path, and this path is the circular helix, not a closed. Okay. I cannot show you the simulation for this example because this is the three-dimensional vector field, and it becomes very crowded, and it's really hard to visualize it. And take up a lot of memory to actually put that on the screen. But basically, what you have is, let's say this is three-dimensional vector field, and you have helix like going like this. All right, and it's immersed inside a fluid. So you can think of this as a DNA. And always double helix, double string helix. But let's say if the DNA is immersed inside a fluid flow inside your body, and this is what you're going to calculate the flow field, the fluid flow. Yeah. Okay. So I was at the University of Cincinnati many months ago, and I worked on this project that's exactly what happened, that I use this kind of integral to calculate the flow field, the interaction between the helix or the DNA. So there's two helixes inside a fluid flow box. And not only that, we let a current or the magnetic field flow through the fluid. And doing that, the DNA actually curve together and create a ball. So it's a very cool project. We didn't get anywhere with that. We have the model, the math model, but we cannot match the result that we get with the experiments that another group at Pittsburgh University of Pittsburgh that provides. So we just abandoned the project at the end, unfortunately. But it's a very cool project. Anyway, so you have the fluid, you have the vector field, you have a curve, in this case, the helix. Let's calculate the flow field. So the flow integral is equal to the line integral of f dot with t ds. But again, in practice, we're not going to use this formula to calculate, but instead we use the definite integral, in this case from 0 to pi over 2 of f dot with r prime of t dt, where you have that r of t is equal to cosine of t, sine of t, t, or r prime in this case is negative sine of t, cosine of t, comma 1. Not only you parameterize the curve, you also have to parameterize the vector field as well. So f is equal to x, z, and y. For x is equal to cosine of t, z is equal to t, and y is equal to sine of t. So the flow integral becomes 0 to pi over 2 of f, in this case cosine of t, t sine of t, dot with r prime is negative sine of t, cosine of t, comma 1 dt. All right. So we manipulate the integrand and see what we got here. So integral from 0 to pi over 2 of negative sine of t, cosine of t, plus t times cosine of t, plus sine of t. So you don't have to do the calculation. I'm going to give you the answer. Again, at this level, we care more about setup, and even though we can say a lot of things about this, but let's not focus too much on the calculation. So obviously, we're going to break this integral down into 3 different integrals. So the first integral is the integral from 0 to pi over 2 of negative sine of t, cosine of t dt, plus the integral from 0 to pi over 2 t times cosine of t dt, plus the integral from 0 to pi over 2 of sine of t dt. So for the first integral, you use integration by substitutions, even though it's a function, but not symmetrical. Or so you have to have the balance. The second integral, you have to use integration by parts. And the last integral is just a regular basic integral. So let me note that, so the first integral, you have to use integration by parts. Integration by substitutions. The second integral is integration by parts. And again, the last one is just some basic integral. The first integral will give you negative 1/2. The second integral will give you pi over 2 minus 1. And the last integral give you positive 1. Now altogether, the result is pi over 2 minus 1/2. And when you calculate it out in decimal number, you also have a positive number, positive results. It's indicate that if you move along the fluid velocity, move along the fluid flow, you move in a positive directions along the helix because you have a positive result here. If you have a negative result, then you move against the flow. Cool with this? Right, so that's the applications of line integral along inside a vector field.